Hello, good evening. I hope I am audible to you.
Yes,
Am I
sir.
audible? Okay.
Sir.
Yeah. So we'll start now. So my name is Ranjan Bora and I am one of the TA in this course, Biomechanics of Joints and Orthopaedic Implants. And today is the tutorial for week 6. And previously I have taken tutorials starting from week 1 to week 5. And those tutorial videos are available in my YouTube channel, and the link to those YouTube videos you can find from the NPTEL web page of this course. So first today I'll solve the assignment from week 5, which was given in the last week. And after that, I will discuss some concepts from week 6, like the finite element analysis. What is the finite element analysis and how we can solve any problem using the finite element analysis. And also I will show some software demonstration using the finite element analysis in the ANSYS software. So let's start. First, I will solve the assignment from week 5. So this was the first question. Like it is asking about what is a tensile strain. So
A.
yes, A is correct. In the last week, I have discussed like strain is the change in length divided by original length. So here you can see in this picture there is a rod and we are applying an axial load on both the ends. So because of the applied load, its length will be increased, and this parameter, change in length divided by original length, this is known as strain. And next question is the materials which have the same elastic properties. Yeah, yes, isotropic. So you can see this is a picture. This is a picture of isotropic material, like in all the 3 directions, X, Y, and Z. Here A means a physical property. Like in all the directions, the property is A. Like it is not getting changed. But in an isotropic material, you can see the properties are different in all the 3 directions. In one direction it is A, one direction it is P, and one direction it is C. So same elastic properties, isotropic materials have the same elastic properties in all directions. And the next question, bone is a, what type of material is a bone? No, bone is not an orthotropic. Bone is an anisotropic in nature. So you can see there are different groups here which are present in the bone. Like later we'll discuss, like there are some tensile groups and compression groups. Because of the different groups in the different parts of the bone, it behaves like an isotropic material. Means its properties are not same in all the directions. In all the 3 directions, the properties are different. That's why it is an anisotropic material. And next question, number of independent elastic constants for an isotropic linear elastic material is 2. And you those independent elastic constants, like one is the Young's modulus, and another one is the Poisson's ratio. So these are the two independent elastic constants. It is represented with E and it is represented with mu. Okay. And in this question, we'll see like an isotropic nature of bone proximal femur arises from the, what are those groups? Yes, A, tensile and compressive. So you can see, like in the previous slide, we have seen these are the groups. So here one between 1 and 2 there is PC. PC means primary compressive groups, and here between 3 and 4 there is PT, which are the primary tensile groups. So because of these different groups, so it is an isotropic material, and yeah, so these are the two groups, tensile and compressive. And next is explicit modeling of trabecular bone can be achieved using test models, but these models are computationally expensive. Yes, A is correct. Micro FE, micro finite element. Like you can see, this is one example of a micro finite element model of proximal femur. And like what we do in the micro finite element, in the previous slide we have seen there are different groups, right? Tensile groups and compressive groups, and their structures are different. So means using the micro finite element, we can model these structures inside a finite element model. So you can see, means to define these structures, we need a very computationally expensive model, which is the micro FE model. So option A is correct. And this is the mineralized tissue mass per total volume of tissue. What is the answer?
B.
Yes, B is correct. So you can see bone has a two-phase. Bone is a type of two-phase porous material. One is solid phase, which is composed of mineralized bone tissue, and one is a fluid phase, which is composed of blood vessels, blood, marrow, and interstitial fluid. And the apparent density is the mineralized tissue per total volume of the tissue. So B is correct. This question, stress is which order tensor? In the last class, we discussed about tensor and about stress. Yeah, D is correct. Stress is a second order tensor. And stress is defined as
B.
yes, internal resistive force per unit area. Like you can see, this is a bar and we are applying, this is the applied force. And because of the applied force, there are some resistance force which are getting produced inside the bar, and this is called stress, the resistance force per unit area. And you know, this is a numerical problem. Based on the given stress tensor, what is the first invariant?
B.
Yes. Yeah, B is correct, but I'll show the how to solve it. So here it is a 3 by 3 stress matrix is given, means in 3-dimensional stress matrix is given. So we can generalize, we can write this matrix in terms of the generalized notations, stress notations, like this is sigma xx, tau xy, tau xz, tau xy, sigma yy, tau yz, tau xz, tau yz, sigma zz. And in the last class, we have discussed that the first invariant, it is given by sigma xx plus sigma yy plus sigma zz. So if we substitute the sigma xx is 1 plus 6 plus 1 equal to 8. So B is correct. Now next question is, based on the given stress tensor, which one of the following options is a principal stress?
C.
Sorry, what? Can you please repeat?
C.
Yeah, C is correct. But again, I will show how to do this. So again, we'll write this the generalized form, sigma xx, tau xy, tau xz, sigma yy, tau yz, tau xz, yz, sigma zz. So, like, to solve this problem, one method is, like, we can write the characteristic equation of stress, which was sigma cube minus I1 sigma square plus I2 sigma minus I3 equal to 0. So if we solve these equations, then we get to know the principal stress. But there is another way of doing this problem, like the simplified method is, see here, we can see that there are some zeros, like this is 1 0 1 0, and where are these zeros located? So this tau xy is 0, tau xy 0, tau yz 0, and tau yz 0. Means, what does it mean? Like, if we take this x, y, and z, and if we take any plane here, any plane means any plane which normal is in the directed in the y direction, and this plane is lying on the xz plane. So this is x and this is z. So here you can see there is no shear stress exists in this plane. If you draw this plane, and now if you draw the component, like it is the tau yx, and it is the tau z, should be tau yz. Okay. So first notation denotes the plane. That's why I have written y, and x denotes the direction in which the stress is acting. And similarly here, tau yz means tau y means denotes the plane, and z denotes the direction. So here from this matrix, we can see that tau yx is 0 and tau yz is 0. That means in this plane, which is perpendicular to the y-axis, there are no shear stress present. Only there is this normal stress, which is sigma yy. So this sigma yy is a principal stress. So we have seen in the last class that the principal stress is normal stress in which there is no shear stress. So in this case, in this plane, there are no shear stress and there exists only one normal stress. So this sigma yy, this 6 is a principal stress. Okay. Okay, coming to next question, what is strain? Like we have
B.
Yeah, change in length to the original length. The first question was also like this. Change in length divided by original length. The materials which have the, again we have solved this problem previously. Which have the, what is the option?
B.
Yes. The materials which have the same elastic properties in all directions are called isotrope. And which number measures an object's resistance to being deformed elastically when stress is applied to it?
B.
Yes. So what is the elastic modulus? Elastic modulus is stress divided by strain. So last class we have seen the stress strain plot, stress strain plot for a ductile material. Like initially, this stress is proportional to strain, and after that there is some plastic deformation, and again the stress increases, and at a point comes when the materials get fractured. So, and the slope of this linear part is called the elastic modulus. So it measures the resistance to being deformed elastically. Means when we increase the strain, the stress is also getting increased. So as the length increases, we need to apply more force for increasing the length. And the why we need to apply the more force? Because there are some resistance which is being resistance which is being applied internally within the material. So yeah, elastic modulus is correct. Number of independent elastic constants for an orthotropic linear elastic material.
C.
Yeah, for orthotropic material, we need to means there are 9 independent elastic constants. Again, this question we have seen, although computationally expensive, which models help in explicit modeling of trabecular bone?
A.
Yes, micro-FA models. Now, apparent density is the, again we have seen this question, mineralized tissue mass per total volume of the tissue sample. So option A is correct. Now this question, endurance limit is the stress level below which an infinite number of loading cycles can be applied to a material without causing. What is the answer?
C. C.
Yes. So you can see this is the plot for a this is the plot for a fatigue loading, like when there is a specimen and we apply some repetitive load, like loading and unloading in this specimen. Means there is some experiment which performed, and means this plot was getting again. This plot was again produced after performing some experiment. So means and so if we plot this trace with respect to the number of cycles, you can see there is a limit, endurance limit, below which if we apply this trace, then the material can sustain infinite number of cycles, infinite number of loading cycles. But above this safe above this endurance limit, let's say if we apply a stress of this amount, means repetitive stress of something like this, then the material will sustain only means the life of the material will only be up to this number of cycles. So after this number of cycles, the material will be material property will be getting failed. So this limit is called the endurance limit, and yeah, it is coming from the concept of fatigue failure. Okay. Next question is the tendency of a solid material to deform permanently under the influence of persistent mechanical stress.
A. Grip.
Yes. So again, this is the plot which is generated, which was produced after doing the creep test. So in the creep test, we apply a constant stress. Means stress remains constant with respect to time. And for the constant stress, if we plot the strain with respect to time, then we can get this type of plot. Like first, there is some instantaneous increase in strain, you can see, and again after that, and there are some plastic deformation in the material. So this strain is called creep strain, and after some time there is some elastic recovery and inelastic recovery, and there is some amount of strain which remains permanently in the material. And so this tendency of the material means to restore the permanent strain is known as the creep. And next question is, due to the viscoelastic properties, stiffness and strength of bone. This is the answer.
B. B.
Yes, B. So this is the plot here. This strain rate is greater than this strain rate epsilon 2. So and the stiffness is the slope of this curve. Slope means the slope defines the angle with respect to the x-axis. So you can see this angle is more than the this angle. That's why means if the strain rate increases, the stiffness also increases, and the strength means the stress. The maximum stress that a material can bear without getting failed is called the strength. So this stress limit also getting increased. That's why both the stiffness and strength of the bone is increased with the increase in strain rate. So this was the questions from the last week assignment. So now I am going to explain about the finite element analysis. What is the finite element analysis and why do you use the finite element analysis? Okay, so finite element analysis or finite element method. So the finite element method is a numerical method for solving problems of engineering and mathematical physics. And for physical systems involving complicated geometries, loadings, and the material properties, it is generally not possible to obtain analytical mathematical solutions. And that's why we use the finite element formulation. The finite element formulation of the problem results in a system of simultaneous algebraic equations for solution. So here are some examples where finite element method is used in solving the biomechanics problem. So you can see this is a example of two femurs. So and this is example of mandible. Here for testing the strength of this plate implant, this mandibular plate, we can use the finite element method. And here is the result of this finite element simulation for this case. So like this, for different applications, means for different loading scenarios in the biomechanics, we can use finite element analysis. Now I will tell about the methods to derive the finite element equations. So there are three primary methods that can be used to derive the finite element equations of a physical system. And one method is the direct method or direct equilibrium method. Like this equilibrium method means which we have discussed earlier, like summation f is 0 and summation m is 0. So we can directly use these equations for solving for solving the finite element equations. And there is one more method which is the variational methods, consisting of the energy methods and the principle of virtual work and the weighted residual methods. So these two methods little bit complex, so I will not explain these two methods. I will explain only the first method. So now coming to the general steps of the finite element method is like what are the steps we need to follow for solving any problem using the finite element method. So first step is to discretize and select the element types. Here are different cases like one-dimensional case, two-dimensional, and three-dimensional case. So you can see for one-dimensional case, we can use one-dimensional elements. Here are some standard elements which are available for doing the finite element analysis. Like one example is spring and one is bar element. And in two-dimensional case, we can use the two-dimensional elements, which are triangles and quadrilaterals. And for three-dimensional elements, we can use tetrahedrals, regular hexahedral, and irregular hexahedral. So today I will give you the demonstration of three-dimensional finite element analysis. Since it is the whatever the cases we see in the biomechanics, all are the three-dimensional cases only. There are no two-dimensional, no one-dimensional case. So yeah, I will give you a demonstration at the end using the ANSYS software. And step 2 is we have to select the displacement function. Like we can select either linear, quadratic, or cubic displacement function. And step 3 is we need to define the strain displacement and stress strain relationships. So here strain is the change in length divided by original length. Here du is the change in length, and it is the original length. And this is the stress strain relationships, which comes from the Hooke's law, which states that stress is directly proportional to strain. And next step is derive the element stiffness matrix and equations. And step 5 is assemble the element equations to obtain the global equations and introduce the boundary conditions. So means in a finite element problem, there are not there are not a single element present. It is not a single element problem. In the finite element, we have finite number of many elements. So first step is uh, to write the element level equations, to write the equations for all the elements. And in the next step, what we do, we assemble all the equations, all the element equations into one global equations, and we apply the boundary conditions. So global matrix equation is obtained by assembling the element level equations. Here matrix sign is not coming. Here ku equal to f. So this is the global matrix equations, where K is the global stiffness matrix, U is global displacement vector, and F is global force vector. Now, we need to also determine the size of the global stiffness matrix. Like in a problem, if there are two elements, then the size of the global stiffness matrix will be, for a one-dimensional problem, the size of the global stiffness matrix will be 2 by 2. For a one-dimensional problem, if there are three elements, then size of the global stiffness matrix will be 3 by 3. So how we determine that size of the global stiffness matrix? So there is one formula here. First, we determine the total number of degrees of freedom in the system. So how we determine here, degrees of freedom per node in multiplied by the total number of nodes. Okay, for example, this is a spring element. Here we have two nodes, 1 and 2. And for a spring element, this is a one-dimensional element. That means it has, in each node, it has 1 degree of freedom. So here degrees of freedom per node is 1, and total number of nodes is 2. So for this spring element, the size of the global stiffness matrix will be 2 by 2. Okay, like this, we determine the size of the global stiffness matrix, which is n by n. N is the total number of degrees of freedom in the system. And size of the global force vector is n by 1. Now, after getting the global stiffness, global matrix equation, next step is solve for the nodal displacements. And after getting the nodal displacements, we can solve for element forces, stress, and strains from this equation. Okay. So now I will show you an example of stiffness matrix for a one-dimensional element, like the stiffness matrix for a spring element. So first step is we need to select the element type. So here you can see there is a spring. A spring, it has a stiffness of K, and it has two nodes, 1 and 2. And in the two nodes, U1 is the displacement in node 1, and U2 is the displacement in node 2. And F1 is the nodal force in node 1, and F2 is the nodal force in node 2. Now, steps 2 and 3 are define the strain displacement and stress strain relationships. So this is the displacement relationships, like the displacement, if we denote the displacement in the spring by delta, then the total displacement will be U2 minus U1. And the spring force, this is spring force T equal to K delta. K is the spring constant. So here we substitute the delta U2 minus U1. Now we need to derive the element stiffness matrix and equations. So here we can write K U2 minus U1 equal to T, which we got from this slide. T equal to K U2 minus U1. Now, if we compare the nodal forces in the above two figures, then we get F1 equal to, like here you can see F1 and F2 are in this direction, the positive x direction. So F1 will be minus T and F2 will be plus T. Here you can see this is F1 and this is F2. Okay, now if we substitute, if we substitute this T equal to, in these two equations, we get this K U2. From the first equation, we will get minus K U2 minus U1 equal to F1. And from the second equation, we will get K U2 minus U1 equal to F2. Okay, now, so we have got two equations from this from the nodal forces F1 and F2. Now, if we write the resulting equation in the matrix form, then it will be, see, first equation was minus K U2 minus U1. So if we multiply here, minus, if we take minus inside the bracket, it will be U1 minus U2 K equal to F1 and minus U1 plus U2 K equal to F2. Now these two equations we can write in matrix form like this: 1 minus 1 minus 1 1. K will be, K we have taken out and here it will be U1 U2 equal to F1 F2. Okay, so this is the equation in matrix form. So in this slide, I will write K one minus 1 minus 1 1 U1 U2 equal to F1 F2. This is the element level equation. This is the equation for one element. Now here K is the stiffness of spring, U1 and U2 are the nodal displacements, F1 and F2 are the nodal forces. So in the matrix form we can write K U equal to F. Okay. Now the next step is to assemble the element equations to obtain the global equations and introduce boundary conditions. So here K is the global stiffness matrix, U is the global displacement vector, and F is the global force vector. So again, we can obtain the total number of degrees of freedom in the system using this equation. And so size of the global stiffness matrix will be n by n, and size of global force vector will be n by 1. Okay, now I will solve one problem using the equations which I have just which we have just seen. So here two springs are given. Assemblies of spring has been shown below. For the load and boundary conditions, we need to find out the nodal displacements and force in each spring. Okay, so what was the element level equation for a spring? The element level equation was K 1 minus 1 minus 1 1 U1 U2 equal to F1 F2. Yes, this was the equation. So here there are two springs. So for the first spring, first spring or first element. What will be the equation? It will be K1 1 minus 1 minus 1 1. Here it is U1, U2, and U3. And the nodal forces are F1, F2, and F3. Okay. U1, U2 equal to F1, F2. And for the second spring, it is K2 1 minus 1 minus 1 1 U2 U3 equal to F2 F3. So we have got the element level equations in terms of in the matrix form. So now what we need to do? We need to form the global equations, global matrix equations. So to form the global matrix equations, we need to make one table like element and the connectivity nodes. So here you can see element 1 is connected with node 1 and 2. 1 and 2, and element 2 is connected with node 2 and 3. And here first we need to find out the size of the global stiffness matrix. So size of global stiffness matrix it was n by n, where n was the total number of degrees of freedom. N is like you can see here, the total number of degrees of freedom equal to degrees of freedom per node into total number of nodes. So here we have 3 nodes, right? 1, 2, and 3. And degrees of freedom per node is 1. So it is 1 multiplied by 3. So n is 3. Therefore, size of the global stiffness matrix is 3 cross 3. So means the global stiffness matrix was K U equal to F. Okay. K is the global stiffness matrix. So it is of size 3 cross 3. First I will write here 1, 2, 3 and 1, 2, 3. So you can see this table. This element 1 is connected with node 1 and 2. So the stiffness matrix for element 1 will be placed in the position 1, 2, 1, 2 only. And since the element 2 is connected with node 2 and 3, so the stiffness matrix for element 2 will be placed in 2, 3 positions. Okay, so for element 1, the stiffness matrix was, if we take K1 inside, if we multiply, means this 1 minus 1 minus 1 or K1 is given 1000. So for the first spring, it will be 1000 minus 1000 minus 1000, 1000 is 1000 minus 1000 minus 1000, 1000. So it was for it was the stiffness for first element. Now, what was the stiffness for second element? Second spring, it is K2 multiplied by 1 minus 1 minus 1, 1. And K2 is given 3000. So here we will write plus 3000. Then it is minus 3000. Minus 3000. And here it is 3000. And the remaining places in which we can place 0 and 0. So we have got the global stiffness matrix. Now we can write U as U1, U2, U3 equal to F. We can write F1, F2, F3. Because this, you can see the size of global force vector is n by 1. N is the total number of degrees of freedom. So now we need to solve this matrix equation. Then we'll get the values of U1, U2, and U3. Okay, so we'll simplify it. Here we'll write 1000 minus 1000, 0, minus 1000, 4000, minus 3000, minus 3000, 3000, 0. It is multiplied with U1, U2, 3 equal to F1, F2, F3. Now we'll substitute these boundary conditions. Here you can see U1, this node 1 is fixed. Node 1 cannot move. So U1 is 0. Okay. And there are no force which is acting on this node 2. So F2 is also 0. F3 is given 100 Newton. Okay, so we'll put U1 0, F2 0, and F3 as 100 in our equation. So we have to write minus 1000, 4000. U1 is 0, U2, U3 equal to F1. We can write small f1, then f2. There is no force in the node 2, and f3 is given 100. So after doing the simplification, we can see we have two unknowns, U2 and U3. Sorry, we have three unknowns, U2, U3, and F1. So from this we'll get three equations, three unknowns, so we can solve this problem. Now I will multiply this matrix with the U1 matrix, and from there we will get three equations. We'll get, if we do the multiplication, we'll 1000 cross 0 minus 1000 dot U2 plus 0 cross U3 equal to, okay, I will write in the matrix form, equal to F1, and the second equation will be minus 1000 cross 0 plus 4000 dot U2 minus 3000 dot U3 0, last equation 0 minus 3000 dot U2 plus 3000 dot U3 is 100. Now we can write these equations as minus 1000 U2 equal to F1, and from the second equation we'll get 4000 U2 minus 0, and third equation minus 3000 U2 plus 3000 U3 is 100. We will number the equations 1, 2, and 3. Now we need to solve these equations for getting the unknowns U2, U3, and F1. So first I will do addition of equation 2 plus 3. If we do this, and you can see this minus 3000 and plus 3000, it will be cancelled. So, and 4000 minus 3000 will get 1000 U2 equal to 100. From here we will get U2 is 0.1. So we have got one displacement, and using the second equation, by substituting U2 0.1 in the second equation, we will get 400 equal to 3000 U3, and from here we will get U3 equal to 4 by 30 will be 0.13. Okay, we have got the displacements U2 and U3. Now we need to find F1. So for finding the F1, we can use this equation 1 and substitute the value of U2 here. So F1 is minus 100 Newton. So now you can see in the figure, we assumed F1 in the positive x direction, but after doing the calculation, we saw that F1 is negative, so the actual direction of F1 will be in the opposite direction. So F1 will be in the opposite direction to what we assumed previously. Okay. So we are applying a force of 100 Newton. You can just verify your answer. We are applying a force of 100 Newton. So we are getting a force of 100 Newton in the opposite direction. That means equilibrium is, the system is in equilibrium. So from this we can say that our calculation is correct. So F1 is minus 100 Newton. Okay, now what do we need to find? We need to find the nodal displacements, which we have found out U1, U2, and U3, and force in each spring. Now we need to find the force in each spring. So what is the force in first spring? Force in first spring, it is given by K1 U2 minus U1. And K1 is given 1000. U2 is 0.1, which we have calculated, and U1 is 0. So force in first spring is 100 Newton, and the force in the second spring is K2 U3 minus U2. K2 was given 3000. U3 was given, we got 0.13. 0.13 minus U2 is 0.1. We'll do this 3000 into 0.03. So it will come 90 Newton. So the force in first spring is 100 Newton, and force in second spring is 90 Newton. So is it clear? Do you want to ask any question?
No, sir.
Okay. So now I will move to the finite element modeling using the ANSYS software. Like what are the steps for doing the finite element analysis in ANSYS? So these are the modeling steps for doing the finite element analysis. First, we need to get the geometries of bones in terms of STL, means in the form of STL file. We can get the STL files from the segmentation, means from the CT scan images using the Mimic software. And after getting the STL file, we can use those STL files, STL geometries, for the FE finite element mesh generation. And then we export the mesh to a finite element software. And finally, we develop the finite element model. Okay, so this is one example which I will show now. Like this is a femur. You can see this is intact. This is healthy femur, and this is the hip joint reaction force of 1500 Newton, which is acting in the vertically downward direction. And this is an implanted femur. Means there's some orthosis or some kind of disease in the femur head. So the surgeon has placed an implant. Now, if the same load of 1500 Newton acts on this implant, what will be the difference in stress distribution in the femur? So that study I will do now. I will show you how to do it using in the ANSYS software. So this is the ANSYS software. Is my screen is visible?
Yes, sir.
Okay. First, I will show you how we'll get the results, like what type of results we will get. So we'll get the maximum principal stress in the intact femur like this. Then we'll get the maximum principal stress in the implanted femur. Here you can see we have dissected the femur here. We have cut the bones and then placed the implant. And lastly, we'll get this von Mises stress in the implant, hip implant. So now I will show the steps how to do the finite element analysis. So in ANSYS, you can see in the left side, we can do different types of analysis. Like we can do some like fluid flow, like CFD analysis, or some vibration analysis, and the static structuralist for the stress analysis. So yeah, for different purpose we can use the ANSYS software. So today I will show you the stress analysis using the static structural. So here you can see these are the steps we need to follow for doing the static structural analysis. First is the engineering data, means first step is to define the material. Like if you click the engineering data, you can see various types of materials here. Like there is one standard material which is structural steel. Here we can add a new material. We can create our own material. So the material for bone is not available in this repository. So the given material property for bone, which is cortical bone, which is Young's modulus of 20 gigapascal and Poisson's ratio of 0.3. First, I will create that material here. So I will give one name, cortical bone. And then in the left side, if we expand these properties, you can see these are the properties we can assign, like isotropic elasticity, orthotropic, or anisotropic. So cortical bone, we will model as the isotropic material. So here you can see in the isotropic elasticity, we need to define the Young's modulus and the Poisson's ratio. So for defining the Young's modulus, first we need to select the unit. So we'll select the gigapascal unit, and the Young's modulus for cortical femur is given 20 gigapascal, and Poisson's ratio is 0.3. So first I will assign here 20 and Poisson's ratio 0.3. So this material is created, cortical bone. Again, there is one more material which is the hip implant. This is the properties for a titanium alloy. So now I will create this material. This is titanium alloy. Okay. Again, I will assign the Young's modulus. Young's modulus is given 110 gigapascal and Poisson's is 0.3. So is 110 gigapascal, Poisson's is 0.3. Okay, so we have defined we have created the materials. Now we can go to the geometry. So there are two cases we need to do. We need to do the finite element. First one is the healthy femur. First, I will show how to do the finite element for healthy femur. After that, I will show this implanted femur. So for doing the healthy femur, we need to import the geometry. So for importing it, we need to right click, then import geometry, browse. Okay, so here you can see this is the like these are some STL files which I which was saved previously from in my computer. So this is the bone. This is the healthy femur. So I will import this bone. Open. So now if we click here, geometry, it will start this space claim. Okay, so this is the femur, healthy femur, which we imported. Okay, but since it is an we have imported in the form of STL file. STL means it is a kind of surface mesh, so we need to convert it into solid. So we need to click here on the left side. Then we need to click here, convert to solid, merge faces. So it has the solid part is converted, means the solid part is generated. Now what we need to do, we need to first save this solid part. We need to save this file in the forms of stp file, which is the standard format for a solid cat file. So we'll save the bone in the form of .stp file. Then we have saved it in downloads only. So we have saved our healthy bone. Now we'll again import the solid file which we have just saved in the .stp format. First we will reset. Okay, now we have deleted that geometry, and now we'll import the this is the file which we just saved bone. STP means it is we can open it using the SolidWorks. That's why it is showing like a SolidWorks application type of file. So we have opened it now. Now we'll go to the model. After clicking the model, it will start the mechanical, ANSYS mechanical, in which we'll do the finite element. Means we'll assign the material property, then we'll apply the boundary conditions. It takes some time. So our bone is imported. You can see. Okay. Geometry bone. So here we need to assign the material. Here the material is coming as textural steel, but we need to assign the material type as a cortical bone, which we have created. So we have assigned the material. You can see the material is now cortical bone, and next step is mesh. So we'll generate the mesh. Since it is a three-dimensional geometry, so mesh type is tetrahedral mesh. You can see this tetrahedral mesh getting generated. Now, what are the boundary conditions? Boundary conditions are we need to fix the bottom part of the femur, and we need to apply a load of 1500 Newton on the top. So here, first we'll select some part from the bottom for applying the boundary conditions. So here we'll create one named selection. For that, first we need to create their nodes. Then here we can change the mode, like for selecting the nodes. Here there are different options like single select, box select, box volume. We'll select here box select, and we'll select the nodes here from the bottom. These nodes are selected for applying the boundary conditions. Now if we return, need to select this side also. Okay, so all the nodes are getting selected from the bottom. Now we need to here click, right click, then create name selection. So if we click on create name selection, then we'll give one name here. We'll give fixed boundary condition. Okay. And again, we need to create another name selection from the top, because we need to apply load here, load of 1500 Newton. So we'll select some nodes. Here we'll click again single select, and we'll select some nodes by simultaneously pressing the control and the mouse left key. We can select multiple nodes. So I have selected this amount of nodes. Again, we'll click right click, then name selection. Here we'll give a name as heap load. So we have created two name selections. Here you can see in the name selections, if we expand, here one is we have created fixed boundary condition, and another one is the heap load. Now we can assign the boundary properties. For assigning it, here under static structural, we need to first right click, then insert. First I will fix the bottom part of the beamer. So for that, we need to insert the nodal displacement. So in the nodal displacement, here name selection, scoping method is name selections. In the name selections, we'll select this fixed boundary condition. Then we'll assign this nodal component, all the components is 0. Means these nodes are constrained, means from all the three directions. They are not allowed to move in any directions. Means they are fixed. So we have applied the fixed boundary condition on the bottom part. Now we'll apply the heap load on the top. For this, we select the heap load. Then here you can see 1500 Newton is in the vertically downward direction. So, and here from this axis, you can see the vertical direction is the Z direction. Okay, so we have to apply the force in the Z component. The X and Y component will be 0, but the Z component we have to apply minus 1500, because this upward is the positive Z. So we are applying force in the vertical negative Z direction. Okay, so now our model is ready. Now we can solve this model, and we can insert what are the stress we are interested in. We are interested in maximum principal stress. So now we can solve. It will take some time. Yeah, the solution is done. you can see this is the maximum principal stress. So now the units are showing in Pascal. So we can change the units here. We can change it into Newton mm. If we change the units, you can see we are getting the stress in the units of megapascal. So this is the contour plots. Like here we are getting the maximum stress. So we can see the location of maximum stress here by clicking on prop. So in the bottom part, we are getting the maximum stress. Okay. So one analysis is done. Next analysis is we need to insert the implant inside the bone, and we need to do the finite element analysis. So for this, I will take one more static structural, and I will directly import the engineering data. So we don't need to create the materials again. We are getting the material data from what we have created already. So now we'll directly go to the geometry. Here the creating the geometry is a little bit different from the previous problem, because here there are two geometry. One is the implant and another one is the bone. So that's why we need to import both the geometry in the form of an assembly. So in the space claim, we have this assembly option. So if we click on assembly, then we need to import both the geometries one by one. First, I will import the here we will select STL. First, I will import the osteomized femur. It is imported somewhere. Yeah, it is here. You can see this is the osteomized femur. This means the top part is cut. The neck part is cutted. This femur. Next, I will import the implant, hip implant. Okay, so here you can see both the parts are imported. So again, we need to convert this both the geometry into solid now, because it is a type of STL files. So we have converted the bone into solid, and then implant into solid. So conversion is done now. Now we need to align, means we need to bring this implant inside this bone. So first we need to align, do some alignment, like we need to move this implant and then we have to place the implant inside the bone. So this alignment we have to do using our mouse. Like these are the axes along which we can translate this implant, and these are the axes along which we can rotate this implant. Okay, it is placed, but the height is not oriented. It takes a lot of time for the alignment. Yeah, this orientation is not proper. So now if we see little bit in this direction. Yeah, I think now it is properly placed inside the bone. Yes. So we have placed the implant inside the bone. Now we need to cut. We need to cut this part of the bone. Means which is we need to cut those part of the bones in which the implant is inside the bone. So for this we need to do one operation here. We need to do this Boolean operation, which is in the design tab. Here we get one option like combine. So here first we need to click on a target object. We have to select the target object this and the cutter object. Here in this case the cutter object is a bone. Sorry, cutter object is the implant. So now now the bone is cut. Okay, this is the bone. We will hide the implant. You can see this part of this inner part from the bone is removed. So and what is this part? So we will keep these two parts. Remaining parts we will delete, and this part also will delete. Okay. So we have kept the we have kept the cut bone and the implant. So again we need to save this model in terms of STP. Save as in terms of STP file. Limit bone implant. Or implanted femur. Okay, we will save. Now again we need to import that STP file. So we'll reset, we'll delete the geometry here and we'll import geometry implanted femur. Now we'll go to the mechanical. It will take some time for importing. Here you can see the implant and bone is getting imported. So now first we need to assign. Okay, first I will change the unit here. I will change it into mm and Newton. And next I will assign the material. For the femur bone, we will assign cortical bone. And for the implant, we will assign the titanium alloy. Now we'll generate the mesh. Again, it will mesh using the tetrahedral elements because it is a three-dimensional geometry. So meshing is done now. Similar to our previous analysis, we'll first select some nodes from here for applying the boundary for applying the boundary conditions. So we'll click box select, then we'll click here and select on the other side also. Then right click, create name selection, fixed boundary condition. Okay. Next we'll select some nodes from the top of the head of the implant. We'll change the mode to single select and we'll select some nodes here. Right click, create name selection, hip load. Okay. Now we can apply the loads. Static structural, right click, insert, and nodal displacement. We have to select the fixed boundary condition. X component is 0, Y component 0, Z component 0. So we have fixed all the nodes from all the three directions. Again, right click, nodal force. We have to select the hip load, Z component minus 1500. Okay, so load is applied. Now we need to insert the stress, maximum principal stress, and we have to insert the equivalent von Mises stress for the implant. So we'll solve it. It will take some time. So result is done now. To see the maximum principal stress in the bone, we can hide the implant. And you can see the maximum principal stress in the bone. Now you can compare both the results. This was for the intact bone, means healthy bone, in which we got the maximum principal stress of around 40 megapascal, but in case of an implanted femur, we are getting maximum of 534, and we are getting maximum at around this point. Yes. Similarly, we can see the von Mises stress in the implant after hiding the bone. Maximum von Mises stress. So the maximum stress we are getting around the neck position, around the neck. So in most of the cases, if you have seen some fracture in the hip implant, in most scenarios, the fracture fracture occurs at this, about this plane. The neck parts gets fractured in most of the hip implant failure cases. because we get the maximum stress around this point, around the neck part. Okay, so this was the analysis. We have seen the von Mises stress in hip plan and the maximum principal stress in the femur bone. So, do you have any question you can ask?
No, sir.
Okay. Then thank you. We'll again meet on next Friday at the same time. So you
Thank
can,
you.
yeah, okay, thank you.